Dear students, Assalamu alaikum. Hope you are fine. Today we are going to have a class on geometrical optics of physics of class 12. Let us see. First of all, I welcome you to my class, and it's me Jafar Iqbal, Assistant Professor of Physics, English Medium Morning Shift, Uttara Model College. Chapter is Geometrical Optics. The first point of this chapter, that is Fermat's principle. What is Fermat's principle? The path followed by a light ray from a certain point to another point, it follows such a path. The time required for this path is minimum or maximum or constant in comparison to the time required for the other paths near to this path followed by the ray. That means when light ray travels from one point to another point in any medium, then it will cover three conditions. It will cover in three conditions, that is, the path will be maximum or minimum or it will be unchanged. That is three conditions. So if the distance of this optical path is L, the time required by this ray to cover it is T, and the speed of light is c, then T is equal to L by c. Here L is the distance covered by the light, c the velocity of the light, and the time required to cover this path, that is T is equal to L by c. In calculus form, that is, here time is constant because the time should be minimum or maximum or constant. The time should be minimum, maximum or constant. That is, time is constant here. That means in calculus, if we differentiate the time with respect to distance, that is dt by x is equal to 0. This is the Fermat principle in calculus form. Now we will go for proving this principle, Fermat's principle. First of all, it came into hypothesis form. Fermat just proposed, but we know that when one hypothesis comes, then the scientist goes for proving it. There are two ways to prove this, that is either experimental proof or the second one, that is theoretical proof. Here we will go for theoretical proof. What is theoretical proof? The theoretical proof is that with the help of established laws or very significant established laws, if we can prove this law, either if we can prove very established laws with the proposed hypothesis, then it is considered that the proposed hypothesis is also accepted, and that maybe that we can accept that as the principle. So here let us see. We know laws of reflection and laws of diffraction of light are two very important and with established significant laws, very ancient laws. So if we can prove these two laws with the help of Fermat's principle, then we can accept this Fermat principle, that is Fermat's hypothesis, as a principle. That is the thing. So let us go here. Deduction of law of reflection with the help of Fermat's principle. See here, light is coming from A, and AP is the incident ray, P is the point of incidence, OP is the normal to the point of incidence. So here APO is the angle of incidence, that is theta 1. Light is reflecting along the path, that is PB. Okay. So here the angle between OP and PB is theta 2, that is the angle of reflection. Here M prime is the reflecting surface, it's a plane reflecting surface. We draw a perpendicular, that is AN on M prime, and it is considered as A. And similarly, we draw another perpendicular, that is BQ, from point B on AM prime. Here, since this angle is theta 1, so this angle will also be theta 1. Why? Because this ray, this line AN and OP are normal to the surface, so these are parallel, and AP is the transversal. So this one and this one are alternate angle. So we know alternate angles are equal. That's why this angle will also be theta 1, and similarly this is theta 2. So this one will also be, this angle will also be theta 2. Here, this distance, that is NP, is considered at x. NP is considered at x, and total distance, that is NQ, this is considered, total distance is D. So PQ is equal to D minus x. Okay. So here the points is explained here. The points. It is detailed here. The MM prime is the reflecting surface, AP is the incident ray, PB is the reflected ray, AN perpendicular to MM prime, and BQ perpendicular to MM prime, theta 1 angle of incidence, theta 2 angle of reflection, and OP normal to the point of incidence. And here AN is equal to, that is AN is equal to A is, and NP is equal to X, PQ is equal to B, PQ is equal to D minus X, NQ is equal to D. And let AP, that is AP, okay, PB, that is PB reflected ray, and perpendicular OP lie on the same plane. Let us consider these three lines, that is AP, PB and OP lie on the same plane. Therefore, the total path covered by the light ray, here light is starting from here and it is coming to point P and then it is going to point B. So total path, that is AP plus PB. So therefore the total path covered by the light ray, that is L is equal to APB is equal to AP plus BP. Okay, that means total path is L. So therefore L is equal to here AP. What is AP? Let us consider here AP. It is a right angle triangle, that is APN is a right angle triangle. So here AP is the hypotenuse, this is side A and this is side X. So AP is equal to root over A square plus X square. And here comes BP. BP is the hypotenuse. So here that is BP is equal to root over B square plus D minus X whole square. That is equation number 1. And we know here the time required is T. So when time required is T, that is T is equal to L by C. But according to Fermat's principle, this value of T is minimum, maximum or unchanged. That is, we know dt by dx is equal to 0. That is, dt by dx is equal to 1 by c dl by dx. We know L is a constant. So if we differentiate this L with respect to distance, then we get 0. So here total term is 0. That is, instead of 0 we can write this one, 1 upon c dl by dx. Okay. Now come, if we differentiate, that is, if we differentiate L with respect to, if we differentiate L with respect to x, then we get these two quantities. Let us consider these two quantities here. Here you see dl by dx. So this term, that is a square plus x square, its power will be half, and then b square plus d minus x whole square, its power will be half. So if we differentiate this one, then the differentiation will be like this. Let us see this here. That is a square plus x square, and its power will be minus half, then 2x, and this half will come here. So 1 by 2c. So c is there. So 1 upon 2c into a square plus x square minus half power, then 2x, plus again 1 upon 2c b square plus d minus x whole square power minus half 2d minus x and if we differentiate d minus x, then it is minus 1 is equal to 0. Okay, so we get this equation, and then here if we calculate, that is here we get these two and these two cancel out. Okay, so we get x by root over a square plus x square, and d minus x root over b square plus d minus x whole square. You see here, that is there is c and there is c. Okay, and on the right side it is 0. So if we multiply both the sides by c, then this c will be cancelled out. In this way c is cancelled out, and these two cancel out, and these two cancel out. So that's why we are getting x by root over a square plus x square is equal to d minus x by root over b square plus d minus x whole square. Okay, now come to the figure x by root over a square plus x square. Come to this figure. Here in this figure you see here, this is x theta 1, the side opposite to angle, that is perpendicular. So x is the perpendicular, and here AP is the hypotenuse. Okay, so perpendicular by hypotenuse, that is sine. So here this is perpendicular, and root over square plus x square, that is hypotenuse. So this is sine theta 1, that is this is sine theta 1. And come to this triangle here, d minus x, that is d minus x, constant angle is theta 2. So d minus x, this is the perpendicular, and here PP is the hypotenuse, and PP is equal to what? Root over b square plus d minus x whole square. That is here perpendicular by hypotenuse, that is sine. So this one is sine theta 2. So we get sine theta 1 is equal to sine theta 2, or if we remove sine from both sides, that is theta 1 is equal to theta 2, that is angle of incidence is equal to angle of reflection. That is the main condition. That is second condition. Second condition of laws of reflection. We know there are two laws. The second law, this is the second law. This is the second law of reflection of light. And we know that three lines, that is incident ray, reflected ray, and OP, just they are lying on the same plane. The figure says that these three are lying on the same plane. So this is the first law of reflection of light. That means this is the first law. So with the help of Fermat's principle, we can prove the laws of reflection. Since laws of reflection is well established law and very ancient law, and we can prove it with the help of Fermat's hypothesis. So Fermat's hypothesis is accepted as also a principle, that is Fermat principle, and this is also accepted. So today we are going to finish the class. In the next class we will come with more topic, that is refraction of the spherical surface, and more topics. So till then, Allah Hafiz, Assalamu alaikum wa rahmatullah.